What do a fleece jacket, water bottle, and seatbelt all have in common? They're all made of polyesters, a strong, light, flexible, and versatile material that you probably interact with every day. The story of how polyesters came to be starts with Wallace Carruthers, working in his lab at DuPont in 1930. Carruthers discovered that mixing alcohols and carboxylic acids led to the formation of fibers, which were polyesters, but he soon invented nylon and stopped all research on polyesters. Two British scientists, Winfield and Dixon, continued Carruthers' work and eventually patented PET, also known as polyethylene terephthalate, in 1941. PET is the most common polyester, and it forms the basis for polyester fibers in clothes and plastic resin used for disposable water bottles. Although PET is the most common polyester, variations can be made by using different alcohols and acids. Polyester fibers can be blended with other materials such as cotton or with different types of polyesters to create strong clothing that is both lightweight and great at insulating. The use of PET in creating plastic bottles for beverages has been game-changing. Plastic bottles are cheap, durable, and recyclable, not to mention lighter and less breakable than previously used glass bottles. From just a few examples of how polyesters are used, hopefully you can see how important they are to modern society. Now that we understand how polyesters are used, let's take a look at how they're made. Polyesters are polymers, which are long chains of repeating units called monomers. Polyesters, as the name suggests, are polymers that have esters as their monomers. You can make an ester through a process called Fischer esterification, which reacts an alcohol with a carboxylic acid, just as Carruthers did. To understand how esters are made, think of our alcohol and acid as Oreos. Imagine that the light cookie represents the alcohol group on the first Oreo, and the dark cookie represents the acid group on the second Oreo. We can remove the light and dark cookies and stick the remaining parts of the Oreos together to represent the ester bond, and the two remaining cookies can stick together to represent the water molecule that is formed. In this analogy, the other two cookies don't represent anything special. Fischer esterification is just like our Oreo example. The carboxylic acid exchanges its OH group for the carbon chain of another alcohol. To understand the how and why of this reaction, let's take a look at the mechanism. The mechanism of the reaction is based on the movement of electrons. Electrons on the double bonded oxygen form a bond with a hydrogen ion provided by an acid catalyst. Electrons from the double bond move to the oxygen. Electrons from the alcohol oxygen then form a bond with the electron-deficient carbon. Electrons from the anion of the acid then bond with the hydrogen, and the electrons from the OH bond move to the oxygen. Another cycle of electron shifting happens when the electrons from the acid's OH group, oxygen, forms another bond with a hydrogen ion to create a water molecule. Electrons from the CO bond move to the water, allowing it to separate. Electrons from the oxygen on the other OH group reform a CO double bond. Finally, electrons from an anion bond with the hydrogen, moving all the electrons from the OH bond to the oxygen. Polyesters are made in a very similar way as a single ester, but instead of using an alcohol and a carboxylic acid, we use a diol and a diacid. Looking back at our Oreo analogy, this would be like having an Oreo with two light cookies and an Oreo with two dark cookies, where both light cookies are alcohols and both dark cookies are acids. When we put these two Oreos together, you can see we end up with a light and a dark cookie on each end of our new Oreo. We can combine our new Oreo with the second one to create an even bigger Oreo. And we can apply this principle to our diols and diacids to form polyesters. In the case of PET, we use ethylene glycol as our diol and terephthalic acid as our diacid. However, many different diols and diacids can be used to create different polyesters. The diol and diacid react using the same mechanism as before, only this time we are left with a molecule that has an alcohol and an acid group. Two of these molecules can react using the alcohol group from one molecule and the acid group from another molecule to form an even bigger molecule with both an alcohol and an acid group. As you can see, these molecules can keep reacting together to form longer and longer chains. Eventually, we have a polyester. However, this isn't the end of the line for polyester creation. Polyesters come out of synthesis very brittle and not very useful, but this can be fixed through heat. Polyesters can be crushed into chips, melted, and then spun into thread. During this melting process, cross-linking occurs. Cross-linking is when bonds form between the individual chains of polyesters to help strengthen the fibers. Another way to change the properties of polyesters is to change the diacid or the diol. If we change terephthalic acid to isophthalic acid in PET, we will create a kink in the polyester chain. This will interfere with crystallization and lower the melting point of the polyester. By changing the diols, diacids, and processing conditions, we can manipulate the chemistry of the polyesters to give us different physical properties in our polyester materials. It's easy to take for granted all of the polyester products we use every day, but hopefully you now have a better appreciation for how amazing polyesters are. Now that you know how they're made and how they can be manipulated, you understand how your jacket and water bottle can be made up of the same thing.